Welcome to Classes with Atish. Today's lecture is Atomic Structure and Evolution of the Bohr Model. Okay, we'll start with J.J. Thomson. So he discovered the electron. So this is Thomson's cathode ray tube. Okay, so in Thomson's cathode ray tube, he had a special coating here. He had two metal plates here, okay, and then he connected these metal plates with a power source like this. This cathode ray tube is vacuum. So what happens is, when this is connected to a power source, what was observed was a ray shot out from the metal plates, okay, and this ray created a glow on this coating, which was a surprise revelation for Thomson. Next, what he did was he put two more metal plates and connected them with another power source, okay, and when he switched on this power source, what happened was this ray bent upwards, which is on the positive side, okay, because this is positive, this is negative. So this proved that whatever this ray is, this is negatively charged and getting attracted to the positive side. More the voltage was increased, more the bend was, okay. So Thomson deduced electrons are very light and they are negatively charged, okay. But he also knew that atom is neutral. So this was Thomson's model of the atom. Thomson proposed that the atom is a sphere which is positively charged, okay, and it held electrons inside the sphere which are negatively charged, so as to cancel out the positive and negative charges. So that's the reason atom is neutral. So Thomson proposed his atomic model in 1898. Few years later, a gentleman named Ernest Rutherford, he did an experiment in 1911 where he bombarded some alpha particles onto a thin gold foil. What are alpha particles? Alpha particles are helium ions, okay, and these were obviously very heavy, positively charged, and very fast, okay. So the setup was something like this. So when these alpha particles were directed to this gold foil, so this is the thin gold foil, this is a radioactive source, and this is the detector. So when these alpha particles were directed to this thin gold foil, the expectation was, if Thomson's model was correct, then this alpha particles will be scattered everywhere, right? It should be scattered everywhere and detected on all parts of this detector fairly uniformly. But what was observed was that the majority of those particles just went through that gold foil and they concentrated on this part of the detector. A few were scattered to the right and left, okay, and even fewer they got reflected back, okay. Okay, So from this model then, it appeared that Thomson's model of a spherical atom which has uniform mass all across with electrons embedded in a positively charged spherical atom, that didn't quite agree with this experiment. So the only way to explain this was Rutherford proposed that there is a very concentrated nucleus which is positively charged. Most of the mass resided in the nucleus, and the electrons were in a cloud, were in orbits around the nucleus. So which means most of the atom is empty space. So that is the reason when this alpha particles were sent to this gold foil, only a few got reflected back, a very few minority get deflected, but most of the others, they went through the atom, and that's the reason majority of those rays ended up here. Okay, so this model kind of agreed with this experiment, and that became Rutherford's model of the atom. So Rutherford's model, there is a positively charged nucleus, and then the electrons are orbiting around the nucleus in fixed circular orbits. So we can imagine an electron here, okay, with a negative charge, and it has a constant velocity, okay, and the radius, Rutherford said, is also fixed radius. So that's how the electron is revolving. Okay. Now let's apply classical physics to this model. Okay. Let's say m is the mass of the electron. R is the radius of the orbit. Okay. So because the electron is moving in constant velocity in a circular orbit, there is a centripetal force, which is, if the v is the velocity, the centripetal force will be mv squared by r. Okay. Now there is also an electrostatic force, of attraction between the positively charged nucleus and the negatively charged electron. Okay, so the electrostatic force is an attractive force between the electron and the positively charged nucleus, and that provides the centripetal force. But this electrostatic force we can write from Coulomb's law, which is Q1 Q2 by 4 pi epsilon naught r square, right? So here we can say electron's charge is E. If the atom's atomic number is Z, then the nucleus's charge is Ze divided by 4 pi epsilon naught r square. Okay. Now because these two are balanced, that's the reason the electron is in orbit. Fc is equals to Fe. So from that we can write mv squared by r is equals to Ze square by 4 pi epsilon naught r square. Okay. So from this we can write the velocity of the electron is root over Z E square by 4 pi epsilon naught mr. Okay. Also, we can say the total energy of this system is the sum of kinetic energy because the electron is in motion plus potential energy because there are two charges in place. Okay. So the kinetic energy is half mv square and potential energy is, so potential energy between two charged particles is given as q1 q2 by 4 pi epsilon naught r. Now the charges involved here are E, but remember these charges we have to consider the sign. Okay, so this becomes minus EZE divided by 4 pi epsilon naught r. Now if we substitute mv square from here, this becomes ZE square divided by 4 pi epsilon naught r minus ZE square by 4. Okay, sorry. So this one becomes 8 pi epsilon naught r divided by 4 pi epsilon naught r. Or the total energy of the system is minus 1 by 8 ZE square by pi epsilon naught r. So far so good, but very soon there were some problems discovered with this model. Problem number 1. Whenever there is a charged particle in motion, they are supposed to emit electromagnetic radiation, right? So if an electron, which is a charged particle, is in motion, then it must emit some electromagnetic radiation. So if that was the case, then this electron, which is, let's say it starts from here, okay, it's revolving around the nucleus, and if it emits electromagnetic radiation, it will quickly start to lose energy and very soon it will fall into the nucleus, right? The model will collapse, but we know that atoms do exist, so definitely there was something missing here. Okay. The other thing that could not be explained was when we look at the absorption or emission spectra, we see there are discrete lines in that spectra for a given gas, right, or a given element. Now this could not explain that. Let me write that out first. Okay. Now if an electron is revolving around the nucleus, it should emit electromagnetic radiation, and this electromagnetic radiation must be continuous. There is no reason why it should be discrete, which means only few wavelengths are emitted, whereas some other wavelengths are missed out. In reality, when we look at the emission spectra or the absorption spectra of a particular element, we see that there are discrete lines. It is not continuous. So this failed to explain, this model failed to explain that phenomena. This topic of the absorption and emission spectra might need a little bit of more understanding. For the benefit of the listeners, I will just put down an example of emission spectra and an absorption spectra of, let's say, hydrogen. And what happens is, if hydrogen gas, it is excited, it emits radiation which has only few wavelengths in that spectra. Similarly, when light is passed through hydrogen, it is seen that some of the same wavelengths which were being emitted by hydrogen before when excited, those wavelengths are missing in the absorption spectra. So just to highlight that, I will put some example on the screen to show you exactly what is meant by emission and absorption spectra. I will put together a different tutorial to understand the emission and absorption spectra in much more detail. Okay? So to address the challenges of the Rutherford model, finally another scientist came into the forefront. His name is Niels Bohr. So in 1913, he postulated the atomic theory. Okay? So what Niels Bohr did was he combined theories of classical physics with quantum ideas. Okay? And he put forward his postulates, which in summary were: so Bohr extended Rutherford's model of the atom, and he maintained that the nucleus is where most of the atom's core mass is. But he said electrons don't move in any random orbits. So he postulated that electrons don't move in any random orbits, but they are confined to some stationary orbits, or we can say some allowed orbits. So why stationary? By stationary, Bohr postulated that when the electron is in that orbit, they can remain in that orbit and not emit any radiation when it is moving around the nucleus. Okay? So with that, he kind of prevented the model in Rutherford's case, where the electron quickly collapsed into the nucleus. Now he says that in that allowed orbits, if the electron is there, then they don't release any energy, therefore it maintains its energy and it can continue to be in that orbit. Now, number two, so the stability condition that was proposed by Bohr, so this defines what are those orbits. So only those orbits are allowed where the angular momentum of the electron in that orbit is an integral multiple of h by 2 pi, where L is the angular momentum of the electron, N is an integer like 1, 2, 3 and such, and h is the Planck's constant. Now we will go into details about why this stability condition actually works, but this is what Bohr proposed. Now, angular momentum of an electron moving in a circular orbit with radius r, and if the electron's mass is m, if it is moving with the fixed velocity v, then it will be mvr. Okay, we can even write that. So mvr is nh by 2 pi. Okay. So these two postulates prevent the electron from collapsing into the nucleus. But what about those spectral lines? like what is this behavior? So let's talk a little bit more about that. So let's say we have I'm just giving you a hypothetical example, a chamber of gas, and this is all pure hydrogen gas. Okay. So let's say this is hydrogen. Okay. So when light is directed to this hydrogen, pure hydrogen gas, the spectral lines that come out are called absorption spectra, which means you will see that overall all the wavelengths will be there except for few which will be blacked out, like this. Okay, so this is the absorption spectra. Okay, similarly, when hydrogen gas is excited and it emits rays, the emission spectra will only have these wavelengths. So in the absorption spectra, these wavelengths are missing, and in the emission spectra, the same set of wavelengths will only appear, everything else will be missing. Okay, so what is this phenomena? So this phenomena is the discreteness of the absorption and emission spectra. Okay, now to explain this, why this happens is Bohr put together his third postulate. So before I write down the third postulate, let me quickly draw maybe the hydrogen atom. So there is one proton in the hydrogen atom, and let's say this is one orbit. This is another orbit. And the electron is in one of these allowed orbits. So this I will mention that these are the allowed orbits, which means when the electron is excited, it will jump to that outer orbit. It cannot exist anywhere in between or any other place. So when the electron is excited, what happens is it jumps to a higher energy level orbit. Okay? So that is what is happening here. When the electrons in the hydrogen atoms are excited because of an external source of light, the difference in energy level corresponds. So if this one was E2, this one was E1, the difference in energy level corresponds to a wavelength or frequency of light that is corresponding to these wavelengths that are missing. So what happens, only those photons of light are absorbed. That's why those particular wavelengths corresponding to that photon of light is missing in the absorption spectra. Only those photons are absorbed, which allows this transition from E1 energy level to E2 energy level. Okay, so that is what Bohr proposed in his third postulate, that atomic transitions can happen only when the difference between the initial energy and the final energy, which we will call delta E, is h nu, where nu again is h is the Planck's constant and nu is the frequency of absorbed or emitted light. So this rule gives the origin of the absorption spectra or the emission spectra of a particular element.
Yeah.
Okay. So from Rutherford-Bohr's model, one thing we can still apply, which is the centripetal force is provided by the electrostatic force between the electron and the nucleus, from which we reach this conclusion that v, which is the speed of the electron, is root over e square by 4 pi epsilon naught m r. Okay, so where m is the mass of the electron and r is the radius of the orbit. Okay, and also we got that the total energy of the system is minus e square by 8 pi epsilon naught r. Okay. Now let's apply the stability condition. So let me rewrite. So angular momentum, okay, of the allowed orbit is an integral multiple of h by 2 pi. Okay, where h is the Planck's constant. So then angular momentum is mvr is nh by 2 pi. On this velocity, we can also include the atomic number. So then it becomes z e square by 4 pi epsilon naught mr. Let's include that, okay? So from this, if we substitute for v, so this becomes mr root over z e square by 4 pi epsilon naught mr is equal to nh by 2 pi. Okay, if let's square both sides, m square r square times z e square by 4 pi epsilon naught mr is equal to n square h square by 4 pi square. Okay, now r and r we can cancel, 4 pi and 4 pi we can cancel. So from this, r becomes n square h square epsilon naught m divided by m. Actually, we could have cancelled this as well, so we don't need this. N square is h square epsilon naught divided by m pi z e square. Okay. Now if we bring all the constants together, then it is h square epsilon naught divided by pi m e square, and then outside we can write n square by z. Okay. Now here epsilon naught is called permittivity in vacuum and h is the Planck's constant. Just to remind you again, z is the atomic number, e is the charge of an electron. Okay, so all these terms are constants. So if that is evaluated and we substitute by a constant a0 n square by z, the value of a0 is 0.53 angstrom. Okay, 1 angstrom is 10 to the power minus 10 meters. Okay, so for a 1 electron system, okay, this is only applicable for a 1 electron system because Bohr's theory really worked well for hydrogen and helium ions. So this is applicable for a 1 electron system. So For an one electron system, Z being the atomic number, let's say in the case of hydrogen, the first orbit of the electron, first stable orbit of the electron is at 0.53 angstrom from the nucleus. That is the radius of the first allowed orbit. Okay. To find the next allowed orbit, substitute n by 2. So that will be 4 times 0.53 angstrom. Okay. And such. So this is called Bohr orbit, or this is the orbit corresponding to the ground state of hydrogen atom. Okay. All right. So let's write this formula on the side so we remember those. So E equals root over Z E square by 4 pi epsilon naught m r. Okay. Radius, or the nth radius is, the full formula, E square epsilon naught by pi m E square n square by Z. Okay. All right. Now, what is the total energy of each of these orbits? So this is, we can say, it defines the energy of those stationary orbits. So we can write minus E square by 8 pi epsilon naught r. Let's substitute the value of r now. In fact, energy also we can include the atomic number, so Z E square. So let's do Z E square here. So minus Z E square divided by 8 pi epsilon naught. And what is R? R is 8 square epsilon naught n square by pi m E square Z. Okay. So pi okay, so this becomes minus Z square e to the power 4 m divided by 8 square epsilon naught square n square. Now we can bring all the constant terms together. So this becomes Z square by n square, and all the constant terms are e to the power 4 m divided by 8 square epsilon naught square. Now when this is evaluated, it comes to minus 13.6 Z square by n square electron volt. Okay. So let's write the energy equation in terms of this. So this is minus 13.6 Z square by n square electron volt. Okay. So what that means is, let's say this is the nucleus. Okay. And we have electrons in orbit. So this is first orbit, this is second orbit, this is third orbit. Okay. Now this corresponds to n equals 1, this corresponds to n equals 2, and this corresponds to n equals 3. Yeah. Bohr also gave name for each of these orbits. So when n is 1, it is called k orbit. When it is 2, L. When it is 3, M. When it is 4, N, and such. Okay. So when the electron is in the ground state, okay, which is n equals to 1, its So N is 1. Let's say this is the hydrogen atom. Okay. So when N equals 1, how much is its energy? Its energy is minus 13.6 electron volt. Okay. Now let's say there is a photon of energy imparted to the hydrogen atom. Okay. Total energy of that photon is 10.2 electron volt. Okay. So to really understand how this works, the electron will absorb this energy only if it can jump to a stable energy level. Okay, either this, or if it can jump to another stable energy level, which is this or the next level and such. So let's say 10.2 electron volt of energy with the photon comes in. Let's see if the electron will or will not absorb that energy. Okay, it can reject it as well. So let's see, 13.6 plus 10.2. How much is it? Minus 3.4 electron volt. Now, does this correspond to any of the higher energy levels? Let's find that out. So we know E1 is minus 13.6 electron volt. E2 will be how much? Z is 1 for hydrogen divided by 2 square, right? So minus 13.6 divided by 2 square, which is minus 3.4 electron volt. So perfect. So then this photon will get absorbed by the electron, because this corresponds to minus 3.4, which is the next energy level, and it will jump to that first excited state. Okay, when it jumps, it absorbs this photon. That's the reason in the light that comes out of this, that particular photon's wavelength is missing. Okay, in the absorption spectra. Similarly, let's say the electron now cools down, it comes back to the ground state. Exactly 10.2 electron volt of photon energy will be released. So a photon will be released, which is light will be released, and you will see in the emission spectra that same wavelength. Okay? So this ground state corresponds to minus 13.6. The next state is minus 3.4 electron volt. Next one will be minus 13.6 divided by 3 square, which is 13.6 divided by 9, 1.51 electron volt and such. So with this, now you can see a very important and exciting conclusion can be made. The conclusion is this, that the absorption spectra or the emission spectra becomes a signature of an atom. So for an hydrogen atom, it will always have a signature absorption and emission spectra, because the energy levels that an electron can get excited to during an atomic transition are very specific to that atomic structure of that element. So from this fundamental finding, we can even find out from a distant star's light, we can find out through spectroscopy what elements that star is composed of. So amazing. So with that, we'll close this lesson for today, And in the next lesson, we'll go into a little bit more details around atomic structure. So Bohr's model only is able to explain simple atoms like hydrogen atom or a helium ion, which has one electron. So it can explain nature of those atoms. But as soon as number of electrons increase, Bohr's model cannot explain everything. For that, we'll go into some other models and discuss those. Okay, cheers.